Okay, welcome to this Scribblecast or video on real number systems. Our outcomes, or what we'd like to do, is look at the different types of real numbers, make sure that you know how to classify them. We'll look at properties of each of the real numbers. Then we'll use set notation to express a range of numbers within the real number system. And finally, we'll just look at one other, I guess, characteristic of number systems, or a concept that's called absolute value. So to begin with, here are the number systems within the real number system. If you want to think of it as a big box of stuff, the whole box would be the real numbers, and then we throw a bunch of stuff inside the box. And some of them overlap, some don't. On the next slide, I'll sort of show you another representation. So it's important to note that all the real number system includes all of these things here. So each of these are a component of the real numbers. So if you pick any number within there, they all belong to the real number system. Okay, the first number system or name for it is the natural numbers. These are the counting numbers, so starting at 1. So 1, 2, 3, etc. They don't include the numbers in between, like no decimals, no fractions. It's just the counting numbers. Whole numbers, same as these ones, but they put a 0 in too. So they include all the numbers, the counting numbers, and 0. Integers are the same thing, so the counting numbers plus 0, but also the negative counting numbers. So you could have -4, -3, -2, -1. Those are the negative counting numbers, and they keep going, of course. And then they also include 0, 1, 2, 3, and all the positive counting numbers. So all of those would be integers. Rational numbers, these are where we get to the numbers in between. But we have to remember that they also include everything from the integers. So they include the counting numbers, 0, the negative numbers, and they include all the numbers in between, like decimals or fractions. When we look at decimals, all fractions would be rational numbers. But with decimals, there are some decimals that aren't rational numbers. We make a distinction between them. If they have a decimal that repeats, then they're rational numbers. If the decimals don't repeat, then they're irrational numbers. Now, just to give you an example, say if you had 1.5, you look and you say, well, there's no decimals that are repeating. But you could actually put a 0 in there, and you could keep putting zeros in forever. Therefore, the 0 is repeating. That's what classifies that as a rational number. But if I had a number like, and here's a good example, pi. You should be familiar with pi. Pi is an irrational number because its decimal place doesn't repeat. It's 3.1415926, and the numbers just keep going and never repeat. So it's an example of an irrational number. Okay, so here's sort of a visual representation of what I was talking about. So the real numbers include all of these things here. They include rationals, irrationals. That's sort of a major distinction, I guess you could, or separation you could put in there. And then rational numbers are composed of integers or rationals that aren't integers, like fractions, decimals. That's what would be over here, fractions and decimals. And then integers are broken up into the negative integers, positive integers, and 0 in the middle. So why don't you take a second, see if you can identify what number systems each of these 8 numbers at the top should go in. You can pause the tape and then I'll sort of give you an idea of what they are after. Okay, hopefully you've pressed play, so let's take a look at 5. So 5, it's a real number. Is it irrational or rational? Oh, let me just drop it there. So it's a real number. Since it has a decimal that repeats, 5.0000, it's a rational number. It is an integer, so I can put it here. It's not an integer. So it's an integer, and it's a positive integer. So the number 5 is actually could be in all of those spots. So it's a real number, rational, integer, and a positive integer. -5 would be the same thing. So it's a real number, it's a rational number, it's an integer, and in this case, it's a negative integer. -2.3, it's real. It's a rational number. But in this case here, it's a decimal or fraction, so it belongs over there. It's not an integer. Okay, here the number e, it's actually an example of an irrational number. So it would be a real number, but it also would be an irrational number. And none of those over there. Negative 2/5, that's a fraction, so it's a real number. And it's a rational number. And it's a fraction. So it's over here with the decimals and fractions. Root 7, anytime you have a square root, not cube root, but I guess cube root too. Anytime you have a radical like this, where the number inside doesn't come out even, like if you had square root of 9, that's 3, that's an integer. But if you have the square root of a number that doesn't come out even, it's going to be an irrational number. Oh, I forgot, it's also a real number. Pi is another example of an irrational number, and we just talked about that. It's also a real number. And 0 would be a real number. It would be a rational number, and it would be an integer, and it would also be I guess 0. Okay, so hopefully that gives you an idea of how those number systems interact. Now, when we're dealing with looking at number systems, one of the things that we often have to do is to classify or group things or express a group of numbers in a short form. And we do that with a number of different ways. We can use a set interval notation or set notation. We can also use interval notation. And let me sort of show you how both of those work. I don't know why those are highlighted. There we go. Okay, so set builder notation looks like this one. So if I say had a question where I said, okay, my answer is everything over 3. Okay, so every number over 3. So rather than writing that, or rather than listing them all out, 3, 4, 5, 6, 7, etc., and maybe I'd like to include the numbers in between, that would be impossible to list all those. So we use this set builder notation to show that. So we can say, okay, my answer are all of the x's, or all of a certain variable, and then we put a straight line there, and this straight line, you can think of it as being as long as. So all these x's, as long as x, I want everything above 3. So as long as x is greater than 3. So that's a way, that's not very good. It should look like that, ish. Let me erase that. Here, I'll put it in nicely. So everything above 3, there. All the x's as long as x is greater than 3. So this is known as set builder notation. Now, lately they've been using another type of notation that turns out that it's quite easy and a little bit simpler than the set notation. It's called interval notation. And your answers in your book will often show your answer this way, so you need to be comfortable with that too. So interval notation, it follows this format where you just have one thing here and one thing there. This thing is where you start, and this is where you end up. Okay. Also, the brackets or the lines that they use in front of the start and the end are significant. If they use one that's a curly one, it means it doesn't include this number. If they use a square one, it means it does include that. So say, for example, I wanted to say, well, this one we did there. So in set builder notation, I have all the x's as long as x is bigger than 3. Okay, maybe to visualize that, I'll put that on a graph. So here's 0, 1, 2, 3. And I want to have everything that's bigger than 3. So where I'm starting at is at 3. So in my set builder notation, I'd put a 3. Not set builder. In my interval notation, I'd put a 3. And then, does it include 3? This one doesn't include 3, so I'd put a curly bracket beside it. And then I'd put a comma. And then it says everything bigger than 3. So this goes up forever. If it goes up forever, then there's not really an end point. And so rather than putting a numbered end, I'll put infinity. So that's the symbol, a sideways 8 is the number for infinity. And for infinity, we'd always use a curly bracket because it doesn't include that last number because there'd always be a number past that. So this, let me just put these in different color. This and this graph here that I drew. Not perfect yet, but they all represent the same thing. To do the graph properly, what I would do is at 3, I'd put a curly bracket like that, and then I'd put a line that extends that way. That's the proper way to do a graph. Let's try a couple. And if you want to press pause and try it, you can. So here's some in interval notation or in set builder notation, and I want to make them into interval notation. I like using a graph to help me out with this. So here's a graph, and it says it starts at -4, and it goes up to a +1. So here's 1. 0 would be in the middle here somewhere. I don't really care about what's in the middle, but I'm starting here, ending there. This one says less than or equal to, so it must include 4. So if it includes 4, I'd put a square thing there. Now I'm going to put a line, and it goes all the way up to 1, but it doesn't include 1. So if it doesn't include 1, there's no equal sign underneath that, then I put a curly bracket there. So right there. That would be a graph that represents this set builder notation. To do the interval notation, that's what I'm wanting to do, is I just sort of copy this. It's at -4 is where it starts. It ends at +1. It includes -4, so I put a square bracket. It doesn't include 1, so I put a curly bracket. Okay, here's another one. All the x's such as x is greater than or equal to the square root of 3. Now square root of 3 is irrational, so it's hard to put that on a graph. So we're just going to have to ballpark it. So if you do square root of 3 on a calculator, it's 1 point something. So I'm just going to ballpark it in here somewhere. So I'll put √3 somewhere in there, but it's not an exact point on the number line because the decimal never ends. So I'm just ballparking it. Now it says greater than or equal to, so I have to put a square bracket somewhere in there. And it's greater than, there's no limit, so this goes on forever. So that would be the graph associated with that. To do the set or the interval notation, I'd say square root of 3, and it's going all the way up to infinity. Infinity always has a curly one. And root of 3, it's equal to that, so I need to put a square bracket there. Okay, hopefully that helps you in identifying those interval notation and set builder notation. Here's just another quick thing. If you have this as a graph, you want to write interval notation for it. Square bracket or a curly bracket, so I'd put this, and that's at -2. That's where this one would start. Looks like it goes on forever. That would be my interval notation for that graph. How about this one? Square bracket, so I'm starting at 0. Looks like I'm ending at 6 here. And it's not including 6, so I put a curly. This one includes 0, so I put a square. Okay? Again, hopefully that helps you out. Now, within all these number systems, or with these groups of numbers, there's properties that we can use to describe things that are happening within the numbers, or operations on the numbers. And they're actually rules that I can use to help me simplify any expression that includes real numbers. So here they are. You may want to write these down, and we'll use them as we go through the course. You'll often hear your instructor talk about the commutative property or associative property or distributive property, and this is what they refer to. I'll just give you a brief rundown of what they mean. Commutative property of addition and multiplication means that if you're adding two numbers, it doesn't matter what one you put first. So you could put 6 plus 3, that's going to be the same answer as 3 plus 6. Same with commutative property of multiplication. If you have 2 times 4, that's the same thing as 4 times 2. Notice those little dots are times, they're not decimals. Okay, in each case you're getting 8. The next two properties are associative properties. These ones are fairly powerful. We use these all the time. And it means that, what it means is that when you're grouping or when you're adding these numbers, it doesn't matter which ones you group and do first. So if all I'm doing is adding, I could, if I wanted, add the B and the C and then add the A. Or I could add the A and the B and then add the C. Or I could, and this sort of gets into commutative too, add the C and the A and the C and then add the B. So it doesn't matter what order that you do that in. So for example, if I went 3 plus 6 plus 4. So if I add the 6 and 4 first, that's 10 plus 3, that's 13. If I added the 3 plus 6 first and got 9, and then added the 4, that's 13. Doesn't matter the order. Okay? Associative property, same thing. This is a powerful property, and again, we use this quite often in simplifying or solving equations. It seems funny, but it's a powerful property. It says that if you're adding 0 to anything, it doesn't change that number. So a plus 0 or 0 plus a, you're just getting an a out of that. So adding 0 to something doesn't change it. Similarly, if you have a positive number and a negative number, and they're the same number, if you add them both together, you get 0. So if I had 6 plus a negative 6, I get 0. If I have a p plus if I have a p plus a negative p, that's a plus, again my answer is 0. So if these two things are the same, one's positive, one's negative, I get 0. Here's a couple other powerful properties. The multiplicative identity property, we use this in solving equations all the time. If you're multiplying by 1, it doesn't change it. A times 1 is still a. 5 times 1 is still 5. Star times 1 is still just a star. Similarly, you have a multiplicative inverse property, where if you take a number and multiply it by its inverse, you come up with 1. So if I have 2 and I multiply that by the reciprocal or the inverse of 2, which is 1/2, 2 times a half gives me 1. Last property is the distributive property, and if you're multiplying a factor by a binomial or by two things inside, what you can do to simplify that is multiply the a first by the b, and then multiply the a by the c and add the results. So if I had 2 times x minus 5, for example, I could go 2 times x is 2x, and then 2 times a negative 5 is negative 10. Okay? So that's an example of the distributive property. Now another concept we'll look at when we're dealing with number systems, and we often use these, is the absolute value of a number. Absolute value, you've probably seen these before where you have like absolute value of negative 5 is equal to a positive 5, and that's true. The concept is that what they're asking for absolute value is really how far away from 0 are you on the number line. And they don't care what direction you're going, if you're going in a negative or a positive or an east, north, south, west direction, doesn't matter. They just want to know how far from 0 are you. So if you're at negative 5 here, you're 1, 2, 3, 4, 5 units away from 0. So they don't care what direction it is, it's just how far from 0 are you. Here's a couple questions. So absolute value of 3, 3's, whoops, that's 4. 3's right there, how far you are from 0? You're 3. Negative 12.5, that's over here somewhere. How far from 0 are you? I don't care which way, you are 12.5 units away from 0. Similar if I had a fraction, 5/8, that would be in here somewhere. How far from 0 are you? You're just 5/8. A good example of using absolute value is if you have to find, for example, the distance between 2 points. So if you have distance between, say, a negative 5 and a 5, if you look on the number line, so here's negative 5, here's 0, and here's 5. If they say, what's the distance between those 2 points? Well, here it's pretty easy to see. I've got 5 plus another 5. It's going to be 10. But I can also use this little formula with an absolute value sign in to help me figure that out. So if I want to know the distance between, I could say, okay, this is the first number. That's negative 5. So negative 5 minus b, the second number is a 5. And I have to take the absolute value of that. So negative 5 minus 5 is equal to a negative 10. And the absolute value of negative 10 is positive 10. So the distance between those 2 points, positive 10. That's how far they are. Here's a couple. Maybe press pause and try and see if you can come up with these. Here's your formula, right? Absolute value of a minus b, or first number minus the second number. Okay, hopefully you press play. Here we go. So this one would be, I'll call this one A and this one B. And it doesn't matter what order you put those in, they'll work properly both ways. So absolute value of -4 minus 11. Okay, -4 right there, minus comes from right there, and b was just a plain 11. So -4 minus 11 that's equal to a -15. Absolute value of -15 is a positive 15. Let me just do that one if I swap the order around. We'll do the same thing. So it'd be 11. Now careful here because it's minus, that's from my formula, but it's minus a -4, right? So 11 minus the -4, the rule is these both change to plus, so now it's 11 plus 4, so it's the absolute value of positive 15, which again is just plain 15. So notice they come in with the same answer. Okay, here's another one. We'll treat this as A and this is B. So the distance between those 2 points, -2/5 minus 8/15. Ooh, fractions. You could pull out the calculator to do that, or if you're good with fractions, this would be -6/15 minus 8/15. -6 minus 8 is -14/15. And the absolute value of -14/15 is positive 14/15. So the distance between those 2 points on the number line would be 14/15. Okay, hopefully those are some concepts that are fairly comfortable for you. If you have any questions, please see your instructor. Try some questions. Here's some from our current textbook that you could maybe try. But any review text would have those.